Okay, let's work with these compound interests and continuous compound interests, logarithms. Just a quick response to your questions. Good questions. So here's a basic exponential function, exponential because the variable is an exponent. The value up front, this is always your initial amount, with the amount you start with. If it's an investment, it's how much you put in the bank. Whether we call it A or whether we call it Y sub 0, it's always your initial investment, because when x equals 0, anything to the 0 power is 1, so this whole thing just becomes a 1 times something. So at time t equals 0 or x equals 0, it's just 1 times A, which means that's how much you start with, A times 1. But nonetheless, let's do a quick logarithm. We cover logarithms in Math 95, the class before this one. And on basic logarithms, if you had, for example, a simple equation, let's just go y equals 3 to the x. This is an exponential equation, and we want to solve for the variable, which is in the exponent. We have to get this out of the exponent position. And so the way we do that is by using logarithms. And every exponential equation can be written as a logarithm by writing this as log. In this case, the base on the exponent is 3, so it's log base 3 of this value y equals x. Every single exponential equation can be rewritten as a log, and every logarithm can be rewritten as an exponential equation. The key here is, if we were to write this as y equals b to the x, we can always rewrite that as log base b of y equals x. And essentially what it's saying is this base would have to be raised to this. We're always solving for the exponent. This is the exponent we'd have to raise this base to in order to get this. So let's do some obvious ones. How about if we do 8 equals 2 to the third power? So 2 times 2 times 2 equals 8. And so if we rewrote this, what we're saying is log base 2 of 8 equals 3, which means you'd have to raise 2 to the third power. This is the exponent. You'd have to raise 2 to the third power to get 8. So every exponential equation can be written as a log, and every log can be written as an exponential equation. So we can rewrite these back and forth. Now, having said that, if we can rewrite every exponential equation as a logarithm, and if we look at exponential equations and we wonder what the base could be, the two most common bases ever used in our application in the real world, first and foremost, base 10, because our number system is a base 10, 1, 10, 100, 1,000. So base 10 is the most common base that's used. So when we look at that as a logarithm, that would be log base 10 of y equals x. And since 10 is the most common base, we always have log base 10. Then when we write this just as a log with no base, we don't put a number here, it's automatically implied to be base 10, because that's the most common one used. So on your calculator, when you see log, it's always base 10, meaning you're solving for an exponential equation with base 10. So 10 is the most common base, so we have a separate logarithm for just base 10, and that's on your calculator. The second most common base that you have is base e. E is it's Euler's number. It's sometimes referred to as an exponential number. E, if you push it on your calculator, you'll see a second shift for E. E is 2.71, and it's a long decimal. In fact, it never ends. It's irrational, like pi. But this is the most common, second most common base that we experience in biology and economics in the real world. That's the second most common base. And so because of that, when we rewrite it as a logarithm, it would be written as log base e of y equals x. And since base e is the second most common used, instead of writing it log base e, we write it as natural log of y equals x. So when you see this ln, it's the same as log. It's just log by itself is automatically base 10, ln is a log base e. So whenever you have an exponential equation that deals with base e, you would use ln. And so we have a separate key on our calculator for that. So the two most common logarithm bases are base 10, so we don't write it as a base, and base e, so we don't write it as a base, and we have separate keys for those. Any other logarithm, we would have to write it as log base 7 of 49, for example, and we're saying what exponent would you raise 7 to get 49, and of course that would be 2. So there's a quick review on logarithms and what's the difference between log and ln. Now to answer your other question, and I'm going to attach a separate Khan Academy video, this is your common exponential equation. Here's your initial amount. Here's your base, which is for exponential growth. This is larger than 1 because you multiply it over and over and over by something bigger than 1, then it's going to get bigger. On exponential decay, it's going to be less than 1 because if you multiply over and over and over by something smaller than 1, then you get less than 1. So when you have, for example, let's just start off with, I'm just going to use some simple numbers, 50 equals, let's just do 5 times 3 to the x, and we want to solve for x, then we're first going to divide by 5, and then we get here and we say, okay, I got to find out 3 raised to what power is 10? Well, 3 squared is 9, so it's close to that. It's a little more than 2, but to solve for it exactly, we would rewrite it as a logarithm by saying log base 3 of 10 equals the exponent x, and now I'm relying on my calculator to do this. I do not have a log base 3 key. I only have log base 10 and log base e on my calculator. I do not have log base 3. Some calculators, though, if you push the math button, it will give you log and allows you to put in the base. The other way to do it is called change of base formula, which is really simple. The 10 is on above the 3 here, so the way you do it is you just use log, that's the regular log, base 10, divided by log of 3 equals x. In other words, you're just splitting this up. Only if you don't have this base and you want to do the numerical calculation on your calculator, you split it up, so you take the log of this one over the log of this one, literally, and you could do that on your calculator. And I'm not going to take the time on this video, but you would simply put this in your calculator using your log keys and come up with whatever number this is. Okay, on to the next one. You had a question of when do you use exponential growth, on compound increasing, decreasing, growth, decay, versus this second formula, and that's what this number 4 box you refer to as trying to do. It says if you're just doing compound, simple compound, then you're going to have y equals a to the bx, because this always stays the same. That means if you're compounding once a year, for example, 15% every year. But if you're doing it more than just once a year, like once a month or once a week, then you use this compound interest formula, where again, this is your principal, your starting amount, here's your ending amount, and this is really just determining what B is, because it's saying, okay, whatever your annual yearly rate is, you're going to divide it by how many times you compound. So if you're compounding monthly, then N would be 12 times a year, and you would put 12 in for N. If you're doing it weekly, then you would do it 52 times a year. So N would be 52. Depends how many times a year, that's N, but 1 is your original principal. Your rate then, if it's, let's say, 12% a year, you're not going to have 12% and earn that every month. You have to take the 12%, divide it by how many times you compound a year, which if you're doing it monthly, you would divide by 12, and that's then your growth or decay rate together. And then over here, T is the number of years, N is how many times every year it gets compounded. So again, monthly or weekly. If you're doing it daily, then this would be 365, and this would be 365. So this is your compound interest problem, and you would do it whether you're doing it monthly, weekly, daily, quarterly, N would be 4, and that's how it would work. But Many things get compounded not monthly or weekly or daily, but continuously. Like, for example, if you put population growth, animal populations you're measuring, the growth and death rate is happening all the time continuously, not just every week or every month. If you put medicine into the bloodstream, it begins to decrease immediately. If you're measuring the lifespan of something based on the carbon dating, then the carbon present is decreasing continuously. So this whole idea of continuously all the time is the difference. And that's where, if you look at how we compute this value of growth or decay B, it comes from this kind of crazy box here where you take your initial amount plus the rate divided by how often it's compounded. That's what this is right here. And if you do something continuously all the time, like populations, then there's technically, it's kind of a calculus thing, but the limit as n approaches infinity, meaning as n gets really, really big, meaning we don't just compound weekly or monthly or daily, we do it every minute, every second, all the time. As n gets really, really big, then what happens is, as it approaches this Euler number, this value e. So instead of using just a base when we're compounding once a year or twice a year or 4 times a year or 52 times a year, if something's happening continuously, then we use this formula. And the only difference is this is still your initial amount they start with. This is the amount you end with. The difference is the base is always E, which is the 2.712 blah, 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 blah. And then you still have the number of years here, but you're using the rate R comes in here, RT. Sometimes this RT is talked about as KT, where K is your rate of, but it's the same whether you use R or K. So the difference is something compounded continuously? If it is, then we use this formula here. And the way that so if you're investing $500 at 10%, so decimal point, for 5 years, then you would use this formula to figure out how much you make. Now, lastly, once you have something compounded continuously, let's say, for example, you're looking for the half-life of something. Well, half-life meaning what you end up with is half of what you start with. So let's say we end up with 500 milligrams. We started with 1,000 milligrams, and we want to find out if K, I'll just make one up, is 0.05. You want to find out how long it takes, T, for you to end up with half of what you started. Now, I wanted to show you how to use logarithms. In this case, the base is E, so natural logarithms. To solve this, we would still divide by 1,000, and we would get 1/2 equals E to the 0.05 T. And we're solving here for T. So now, since the base is E, I would rewrite this using natural logs. So I would say the natural log, that's base E, of 1/2 equals 0.05 T. Now this is a number my calculator is going to give me, so I don't worry about that. I want to find how long it takes. So the last thing then is just to divide both sides by 0.05. So this is a calculator problem. The natural log of 1/2 divided by 0.05 gives me the value of T. So that's purely a calculator problem. So hopefully that helps you decide the difference between something that's just compounded once a year versus compound interest more than once a year, weekly, monthly, versus continuously. That's where we would use this formula with base E on continuously. I hope that helps.